Well, hello again. In this example, you will learn how to include the effects of springs when using virtual work to find deflections of a structure. We're going to be taking a look at this beam. You'll notice there's a couple of translational springs that are providing support for this. Recognize that this roller support, all it's doing is making sure we've got a stable structure, preventing motion from side to side. The springs have an elastic stiffness of 10 kips per inch. We're being asked to use virtual work along with visual integration to solve for the vertical deflection at point B, which is mid-span. Modulus of elasticity, 3600 kSI, moment of inertia, 1500 inches to the fourth. But I want you to recognize that span AB has a moment of inertia of I, whereas BC is only 60% of that. That will most certainly impact the way we approach the solution on this. Basic statics, we can get the reactions here. So 20 kips, and actually there is 0 going on there. Since we are going to be doing some calculations, we need to make sure we've got some consistent units. So simply take this and divide it by 12 to convert it to kips per inch. That will be 1/6 kips per inch as far as the load goes on that. We want to generate the moment diagram. I'm not going to jump straight to the M over EI diagram on this. I simply want to have the moment diagram first so that we can then appropriately handle this variation in the moment of inertia here. So this is my big M diagram, so this is the real structure. And you can follow the procedures for developing moment diagram for this. I'm just going to give it to you here. It's a second order curve where the max value up here can be computed as WL squared over 8, where L is that 20 feet, or in other words 240 inches. The W is the 1/6 kip per inch, and that would compute out to be 1200 kip inches. Okay, we now need to get the M over EI diagram. So we'll come over here. Well, this is the M over EI. And since segment AB has a moment of inertia of I, all I need to do is go ahead and sketch it up just like we did before and divide it by EI. For segment BC, we need to modify that moment by dividing it by 0.6 EI, which would then be 2000 over EI. So look at what our M over EI diagram looks like here, where this is the 2000 over EI. We then need to get the areas, and both of these are second order curves with a 0 slope up here and a 0 slope there. So we can compute A1 with the well-known equation of 2/3 H, 1200 EI, times the width, 120 inches. That will be 96,000 EI. And A2, using the same equation, this time using the values for segment BC. That will be 160,000 EI. We do need to have the centroidal locations, and you can look this up in a chart or any number of resources, but for this shape it is 5/8 the distance. So if the distance is 120 for segment BC, that's what we've got going there, and also here. 5/8 of 120. Before we move on to looking at the virtual structure, we need to make sure that we have identified for our springs the axial forces that are present in there. Quickly using equilibrium, we can identify that the axial force in the spring is 20 kips. It is in compression, so we will use a negative for that. And we'll denote that with the capital letter N, indicating it comes from the real structure. With that, we can now move on to the virtual structure. Since we want to know the deflection at B, we will place a unit load at B in the direction that we want to measure. Let's go ahead and run our statics on this. This is 0.5, 0.5, which will then produce the internal axial force in the springs at being negative 0.5, negative 0.5, and that's once again because they are in compression. We can then generate the moment diagram, and luckily the little m diagram is not based upon the moments of inertia, so we don't have to scale it like we did in the last one, but rather this moment diagram just looks like this with a value of 60. Now you can probably see where that came from pretty quickly here. You've got a force of 0.5 acting over a moment arm of 120. That'll give me the value of 60. What we are going to need on this is we need to know what the value of little m is when we come over here a distance of 5/8 of this 120. So just coming back here, make sure we know what it is we're referring to. And so, using similar triangles, you should be able to get this being 37.5, and in a like fashion, we come over here that 5/8 of that length, and it will also be 37.5. So, the virtual work equation, generically written, if I'm using visual integration, I would take that m, the area of the m over EI diagram, multiply it by the value of little m evaluated at the centroid. But I would also then add my springs, and the way those are is big N times little n divided by KT, and of course I can put a summation sign if I've got more than one spring. Now what is big N? Big N is the axial force in the spring due to the real load. Little n is the axial force in the spring due to the virtual load, and of course KT is the spring stiffness. So we can go ahead and do the calculation that delta B is computed as 96,000, 3,600, 1,500 times 37.5 plus 160,000 divided by 3,600 times 1,500 and that whole quantity will be multiplied also by 37.5. That accounts for the flexural members, the beams, AB, BC. But now what we need to do is we need to include the effects of the springs, and we've got two springs. So big N times little n divided by the spring stiffness. And in this case, since I have two of those, I can just go ahead and do that. If I evaluate that out, 3.78 inches. The positive value says that I have assumed the correct direction back here, so I know that I am deflecting in the downward direction. Now before we close this out, let me draw your attention to something that may be causing you a little bit of grief, in that when we come over here, we use the moment of inertia of 1500, whereas this, we still use 1500 even though when we look back at the original one, we see it like this. That is not to be alarmed, because when we put together our M over EI diagram, we actually made the adjustment of it there, and that's what resulted in that one being a larger value and that one being a larger value. So essentially we wrote our equations so it was consistently in terms of the value of I. And so the fact that you have a different moment of inertia is re-accounted for in that number that's in the numerator. That concludes this example. As always, it's a beautiful day for studying structures.